Hello and welcome to FE exam preparation for mechanical engineers. In today's video, we are going to be doing a review of statics and a short practice problem at the end concerning rigid bodies. So if you remember back to your statics course, statics is the study of objects that are in equilibrium. So that means that the sum of the forces and the sum of the moments applied to the object are zero. So this is going to be your governing equation when approaching most of your statics problems. So when it comes to what kinds of problems that you will actually see on the exam, it could be anything from a particle problem to rigid bodies, which are your things, if you remember, like beams. It could be a bridge with trusses, like so, and then you have some loading. Frames and machines, so frames like an interlocking mechanism with pins and forces being applied. Friction between a surface, and centroids and moments of inertia. So the good news is that a lot of the FE exam problems are going to be 1 to 2 step problems. So it's not going to be some complex system that you're going to have countless lines of algebra to solve, like if you remember to your statics course. These are going to be relatively simple, and you'll see that in the example today. But one thing importantly to note is that all the problems from the particles to friction will use the sum of the forces is equal to 0 and the sum of the moments is equal to 0. Those are going to be your go-to equations. Whereas centroids and moments of inertia are going to be reference book problems. So you're going to want to make sure you familiarize yourself with where these equations are in the reference book, so that way you can just look them up and get the easy points for the shape that they give you. Now, when it comes to how do I approach solving these problems, by far, the most important step is drawing your free body diagram and drawing it correctly. Please, please, please make sure to double check that you are drawing all the forces given in the problem and all reaction forces for the system. Also, make sure that you are defining your coordinate system correctly. Remember, if you're defining a normal Cartesian coordinate system like so, that means that counterclockwise moments will be positive, not clockwise. So just make sure your convention is correct. Also, the next step after drawing your free body diagram is to sum the forces in all directions to 0. Note that for the FE exam, it is highly unlikely that you should see a 3D problem, but it's not completely off the table. So if it's a 2D problem, you'll just have to deal with either X or Y, but if it is a 3D problem, remember to sum the forces in the Z direction to 0. And then after that, if there are any other unknowns that you still need to find, then you should sum the moments about a point to be 0. So if I had a point A, and then B, and then C, you're going to want to pick the point that has the most reaction forces at it, because if you sum the moments about that point, those reaction forces will go away and therefore simplify your calculation. Again, the most important tip that I can provide to anybody studying for the FE exam is that most mistakes happen before the math, so please make sure that you draw a good free body diagram. It is crucial for your success on the exam, and although it might take a little bit longer, it saves you time in the long run, not having to go back and find where you made your mistake. Okay, so let's jump into our first practice problem. So this is very similar to what you could see on the FE exam. It's going to be a rather simple problem statement, such as the one presented here. Determine the reaction moment about point A, or at point A. Not going to be super wordy and full of jumble that you have to read through and sort of figure out. It's going to be very straightforward. And it could 100% be a problem where you have a beam loaded such as the following. So let's jump right on in with the first step of our problem being to draw our free body diagram. So for the sake of this problem, I'm going to use a normal Cartesian coordinate plane with a counterclockwise moment being positive. Again, on the exam, you do not need to do this. You can keep track of it in your head, but for the sake of this video, I'm going to write it out so there's no confusion. Now, when it comes to actually drawing the free body diagram, it's pointless to go ahead and just draw a rectangle. you can get everything and all the information you need just drawing a line for a beam. So if you notice on the diagram, the beam is cantilevered at point A. So this is point A. That means we are going to have a reaction moment in the y direction, AY, and a reaction moment in the x direction, AX. Additionally, we are going to have, reaction force. We are going to have a reaction moment, MA, to counter the forces on the system. Because it is cantilevered, it cannot rotate or translate in any of those directions. Now we can go ahead and draw our forces. We are going to have a 100 kip force right around here, and a 40 kip per foot force right around here. Notice how I'm not drawing the linear distribution of this load. We can actually model it as a point force at the centroid of the loading, and I'll show you how to do that in a second. So now that we have all of our reaction forces drawn on the diagram and our forces, we can go ahead and put in our dimensions. So from point A, because we are going to want to sum moments about point A, that is where most of the reaction forces are, we're going to draw all of our distances and get our lever arms. So this distance was given as 5 feet. Now doing some simple math here, we can figure out that this distance here is 7 feet because the total needs to be 20, and they gave us 5 and 8 feet for the loadings. So 5 plus 7 plus 8 gives you 20. So that means that from point A to this force is going to be 12 feet plus some amount. That some amount is going to be, well, how far from the left-hand side of this triangle here do we have to go in order to find the equivalent point force? Well, if you look in the reference handbook, from the left hand or the right angle side of the triangle, it is going to be 1/3 of the base length. That is where the centroid is, and that is where our point force will be acting for this entire distributed load. So that means that we add 8/3 onto that 12 because it is 1/3 of the 8-foot length. And so tacking that onto the 12 will give us our moment arm for the equivalent point force of that distributed load. Now that we have written out all of our lever arms and have our free body diagram all set up, we can now do the next step, which is to sum forces and sum moments. Well, keep in mind what they asked in the problem statement was to determine the reaction moment at point A. So we do not need to concern ourselves with summing forces in the x, summing forces in the y. That's just a waste of time. So we'll go ahead and sum moments about point A. Now that's going to eliminate forces AY and AX because they are at the point, there's no moment arm. But we're still going to have the reaction moment MA. Then we are going to subtract the 100 kip force times its lever arm of 5 feet. And the reason why we are subtracting the 100 kip force is because this force is going to want to rotate the beam about point A clockwise. It's going to want to create this clockwise rotation that I am making here. So that means that it is negative. The same thing can be said about the 40 kip per foot force. So the way that we handle that is we simply take the 40 kip feet, well, to get the magnitude of that force and keep track of our units, we take the area of the triangle. So that's simple, just 1/2 base times height, the base being 8 feet, and the height being 40 kip feet. Now, should this have been a rectangle, we do length times width, but because it is a triangle, we do 1/2 base times height in order to get the magnitude. Now, keep track of our units here. You will see that this feet and this feet will cancel out, leaving us with kip. And remember, a moment is a force times some unit length. So we need to tack on that 12 feet plus 8/3 feet to get our unit of length. And then there is our moment. So now that we have this equation written out, we can solve for our reaction moment MA. that's going to be equal to 500 kip feet plus 1/2 of 8 is 4. 4 times 40 is 160. And then doing 12 plus 8 over 3, taking 160 times that value on the calculator, you should get 2,346.67 kip times feet. Adding those two values together, you will get that the reaction moment at point A is 2,846.67 kip times feet. And that is your final answer. Keep in mind that the FE exam is multiple choice or free response, so you could be asked to type in this answer or just click the answer choice that is exactly this value or close to it. But by far the hardest part of this problem was the distributed load. So understanding that for distributed loads, you want to take the area in order to get the magnitude, and then also you can model them as a point force at their centroid was the biggest challenge. But as you can see, if you understand how to do that, the actual algebra and the math to get to the answer is only 1 to 2 steps. So thank you so much for watching, and we will see you in the next one.